The next topic then that we'll move on to is optimization. And I'm actually going to use the parametric simulation capability to do optimization. So we'll see more about how to use parametrics in the next example. And I'm going to use the parabolic trough, a parabolic trough design problem as an example for the optimization demonstration. So let me start a new case, a new project. And I'm going to choose concentrating solar power, physical, trough, and in the utility market. And I'll just use the default case name, but whenever you start a new project, you have the option of assigning your own name to the case. So when you're designing a trough system in SAM, the first issue is to determine the optimal solar multiple for the system. So the problem is, the sort of statement of the problem is, given a location, how big should the solar field be? And it's an optimization problem because you want to maximize the system output, but also minimize the system cost. So a larger solar field gives you more energy, but it also costs more. So there's a trade-off between the solar field size and the cost of the system. And the constraint on the problem is, at least at this preliminary stage, is the power cycle capacity. So you're gonna design a system for a nominal capacity. For example, you may want to design a 50 megawatt system. That is determined by the power cycle capacity in the case of a parabolic trough system. So on the power cycle page, you would specify the nominal capacity of the power cycle using these plant capacity variables. And the way it's set up in SAM, the nameplate capacity is this value here, this calculated value, which is in this case 100 megawatts. But you specify the capacity as a design gross value. So if we want to specify a 50 megawatt system, I would type 55 here for the design gross output, and then SAM calculates the nameplate capacity as a product of the gross capacity and this estimated gross to net conversion factor. So that's the first step in designing, in setting up a parabolic trough system in SAM, is to assign the nameplate capacity on the power cycle page. Then the next step, and this is just for a simple system, or a simple analysis, a preliminary analysis, you would probably also be interested in the cooling system type. You can choose between wet, dry, or hybrid. So if you're just getting started modeling trough systems, I think the first thing to do would be to set the nameplate capacity of the power cycle, and then to choose a cooling type. You can just work with the default values at first for the remaining inputs as you're getting started. Then the next step is to determine the optimal solar multiple. And that's going to depend on a couple things. One is the location. So I'm going to, just for fun here, change the location to a location in Spain that has a lower solar resource than the default location of Blythe. So I'll just choose Sevilla in Spain. And then when I go to the solar field page, I need to specify a solar multiple, but I'm not sure what value to use. So I'm going to use the optimization procedure to find the solar multiple value. And for starters, I'm going to model a system with no storage. So on the thermal storage page, I'll change the full load hours of TES to 0. So when I do this, I'm effectively removing storage from the system. So all of these other variables no longer affect the simulation when I change the storage capacity to 0. So for the trough systems, the storage capacity is expressed in hours, and each hour represents the amount of energy that would be required to operate the power block at its rated capacity for a single hour. Okay, so the next step on the solar field, before I can find the optimal solar multiple, I have to choose a value for this irradiation at design point. So this is an input variable that SAM uses to size the solar field. When you specify the solar field size as a solar multiple, SAM calculates the field aperture area based on the solar multiple and this irradiation at design. So basically what it says is, for example, if I choose a solar multiple of 1, the solar field area that SAM calculates would be the field area that would drive the power block at its rated capacity, so in this case 50 megawatts, at 950 watts per square meter. And this calculated field area is displayed down here in the design point variables. This field area would drive the power block at 50 megawatts, given 950 watts per square meter, and accounting for parasitic losses and thermal losses. So SAM calculates a set of design loss values for this sizing calculation that are displayed here in the design point area. The choice of this irradiation at design value depends on your location, and it also depends on your analysis. So there are a number of different approaches for choosing this value, and the folks at NREL recommend using the maximum incident DNI value for this irradiation at design value, but you might want to use a different value depending on the purpose of your analysis. But for this example, I'll illustrate the approach of using the maximum incident DNI value. So to do that, what we're going to have to do is run a simulation, because SAM reports the incident DNI value in the results. It has to have information about the orientation of the collectors in order to calculate the incident radiation. So we could look at the climate page you look at the weather data in the climate page, here we can see the raw DNI data from the weather file. So there's the DNI, direct normal radiation data from the weather file, and we can see that the maximum value here is around 950 watts per square meter. But we want the incident incident DNI value. So for that, we'll run simulations and plot a similar graph of the incident DNI. So once the simulations are running, under the results menu, View Hourly Time Series opens that eView tool, the view graphs of the hourly results. And so what I want to do is to find the maximum value of the collector DNI cosine theta value. This is the incident DNI value. And some of the techniques that I'm showing you here, I'm showing this trough example, but these techniques will be useful across all technologies. So looking at hourly results in the dView data viewer, this works the same across all technologies. So hopefully those of you who aren't modeling trough systems will benefit from this demonstration. So here I'm looking at dView, I'm looking at the hourly tab, and I've selected the collector DNI cosine theta variable. And what I want to do is to find the maximum annual value of this variable. So one way to do that is just to plot the hourly variables, the hourly values, and then to click the zoom to show all data button here down at the bottom right of the window. And so this is January through December. I can see all of the hourly values, and I can kind of pick out the maximum value here, which seems to be around 890 or so. So that's one method. Another method would be to use one of these other tabs. So you can view all this data in lots of different formats on different tabs. I'm going to use the box plot tab, which shows me by month the minimum, maximum, and mean value of any of the hourly variables. So for the collector DNI cosine theta variable, the annual minimum, maximum, and mean values are shown in the last column here. So I can also pick out the maximum value here. And wait, I inadvertently switched the variable here. So we're actually looking at view incident total, which is the wrong variable. I want collector DNI times cosine theta. So the variable name appears in this drop-down list. If I want to pick out the exact value, I can export the data in this table to a text file. So right-click the graph, click Export Data, and I'll just put it on my desktop. And then I can open the text file, and I can read the exact value. Probably be easier to open this in Excel to see the columns, but the annual maximum value is 886 watts per square meter. So I'm going to use 880 as the reference DNI on the solar field page for Sevilla. Okay, so now I have my irradiation at design value. And remember, the question that I'm asking is what solar multiple value should I use for this location? So for that, I'll do an optimization using the parametric simulation capability. So I'll click the pilot tires button and add a parametric simulation, add a variable. It's a variable on the solar field page. Expand the list. These are all the variables on the solar field page that can be specified as parametric variables. And I want the solar multiple variable. There's also a variable here called actual solar multiple, which is a calculated value. That value you can't set the value of that variable. That's a calculated variable and shouldn't really be in this list. So the solar multiple variable is the one that we want to add here. Once you add the variable, then you edit it to assign values to it. So this is a numerical variable. The last example I showed, we assigned the location variable as a parametric variable, and that was a non-numeric variable, so we didn't have this window to assign the values. But most of the variables in SAM are numeric values, numeric variables, and you have this little tool for assigning values to it. So I'm not sure what solar multiple value is going to be optimal. So I will assign a range from 1 to 2.5 in increments of 0.25. So under define range, the start value is 1, end value is 2.5, and I want to increment in steps of 2.5. When I click update, then SAM calculates the series of values that it will assign to the solar multiple variable. So now when I click simulation, SAM is going to run a simulation. I'm sorry, when I click run, SAM is going to run a simulation for each of these variables. So it's going to run 1, 2, 3, 4, 5, 6, 7 simulations. The one thing to note about parametric analyses is that there's no indication on the input page that a variable is being run as a parametric variable. So on the solar field page, there's nothing here that indicates to me that solar multiple is a parametric variable. You have to check here on the parametrics page to see which variables have been assigned more than one value. I click run. Now SAM's going to run the 7 simulations. The one thing to keep in mind as you're setting up parametric simulations is that the more variables you set up as parametric variables and the more values you assign to those variables, the higher the number of simulations and the longer it will take to run. So it's good to be strategic about building up your parametric analysis so you don't waste a lot of time running unnecessary simulations. So choosing the range of values that you think is likely to be within the range that you need is one way to do that. I could have selected values from 1 to 10, for example, but I'm pretty sure that anything above about a solar multiple of 3 is going to be unreasonable, so I don't need to waste simulation time running a lot of extra values. Now the problem the optimization problem here is I want to maximize the system's output and minimize its cost. So a good objective function for that optimization problem is the levelized cost of energy, because the LCOE captures both the energy output and the cost as a dollar per kilowatt hour value. If I choose the solar multiple that results in the minimum LCOE, I can be confident that that value will maximize output and minimize cost. So when we're done with the simulations here, I'm going to plot a graph of LCOE versus solar multiple and pick out the solar multiple that results in the lowest LCOE. So when simulations are finished, Sam shows me the results page, and one of the default graphs on the page here is LCOE versus solar multiple. It's displayed as a bar graph, and Sam happens to report 4 different flavors of the LCOE. The real and nominal, which I discussed briefly yesterday, and then the real and nominal with and without incentives. For the purpose of this analysis, it doesn't really matter which version of the LCOE I use, but I only really need to see one of them. This graph is very cluttered with all 4 versions of the LCOE for each solar multiple value. So I'll right-click the graph to edit it. And I'm plotting results from my parametric analysis, so that the simulation option that I choose is parametric. If I choose base case, then that's going to create a graph of whatever, based on the results of whatever solar multiple value is displayed on the solar field page. So I think the value that I had happened to enter there was 1. So the base case results are for the variables that are on the input pages. The parametric results are going to be for the values that I set up in the parametric analysis. And then I'm plotting the solar multiple for the x-axis, and I'm just going to use the nominal LCOE for the y-axis, and then the bar graph works fine. So as I set up the graph, the graph is actually changing dynamically on the page, so I can check to see how it looks. I think a line graph might be better for this purpose. And then I see there's a legend here that I don't really need, so I'll clear the legend. And I'll add a Y label. So I know what I'm looking at. And then accept. And so from this graph, I can see that the minimum LCOE occurs at a solar multiple of 1.25. If I want to be sure of that, if I'm not sure if 1.25 is lower than 1.5, I can click Show Graph Data and confirm that the minimum LCOE here is at 25.34. That's at a solar multiple of 1.25. In reality, these are very close. 25.34 and 25.38 are very close. So, the optimal solar multiple is probably somewhere. Either one of these could qualify, I would say, as the optimal solar multiple. But I'll choose 1.25. So then if I wanted to proceed with an analysis of a system with no storage, I would go back to the solar field page and change this value to 1.25, and then disable the parametric analysis and proceed with the rest of my modeling of this system. So I could modify other parameters knowing that the solar multiple is optimal for this system. I can further complicate things, however, by adding storage to the system. So in this case, we're modeling a system with no storage. What if I want to design a system with storage? The question there is what's the optimal storage capacity? So I can use a similar technique to optimize both solar for both the solar field area and the storage capacity. So to do that, I would add a second parametric variable, which is storage capacity, and that variable is on the thermal storage page. So I expand the list of variables from the storage page, and full load hours of TES is the name of the variable that defines the storage capacity. And I'll try a range of values from 0 to 12 hours of storage in increments of 4 hours. And so now what's going to happen is Sam is going to run 28 simulations, the 7 solar multiple values and the 4 storage capacity values. So this I'm clicking run and nothing's happening, and that's because I had disabled the parametric simulation. So if I want to run this, the simulations, but when I click run here, it's just running the single case for a solar multiple of 1.25 and storage of 0, which are the values on the input pages. When I enable the parametric simulations, when I click run now, it's going to run 28 simulations. And one thing you'll notice is that it ran through the first 7 simulations very quickly. And that's because the results from my previous runs were stored in memory. So Sam didn't need to rerun those simulations. So it's going to run the 21 remaining simulations so that's a useful thing to know, is that Sam stores results from your previous simulation runs to save you a little bit of time. While we're waiting for those simulations to run, I'll mention the linked parametric option. So there's this button that says set up linkages. And what that allows you to do is to link the values of related variables in a simulation. So if we step away from CFP for a moment and think of a PV example, and let's say we wanted to use parametrics to compare the output of a PV system in 3 different locations. But for each location, we're going to use a different array tilt value. So we want to tilt the array, say, at latitude minus 10 degrees at each of the 3 locations. So to do that, I'd set up a parametric simulation, and I would add the location variable and the array tilt variable to the list of variables. And then I would link the 2 variables so that Sam would only simulate the array tilt value that was appropriate for the location. So rather than, so for example, if I had 3 locations and 3 array tilt values, if I set up linked parametrics, it would run just run 3 simulations rather than running 9 simulations. So the linked parametric option is useful when you have multiple variables and when 2 or more of those variables are related to each other. So I can take a few questions while we're waiting for this to run.
Thank you. At this time, we will begin a question and answer session. To ask a question, please press *1 on your touch-tone phone. Please unmute the line and record your first and last name when prompted. To withdraw the question, please press *2. Once again, please press *1 to ask a question. And one moment, please, while I listen to the name. Your line is open.
Rashmi Shah.
Go ahead with your question, sir.
Yeah, question is, we are talking about the storage. Only TES storage system we can configure it, or can we configure it with the battery too?
So for
the reason, let me give you one scenario. I have a 1 kW load 24/7, and I size my PV system, but I don't know how to size my battery system.
Okay, thank you for the question. So the example that I'm giving now is for a parabolic trough system. And for parabolic troughs, the storage option is thermal energy storage, TE.
No, I agree. Yesterday I missed that question. Otherwise it was yesterday's question.
And then for PV systems,
yeah.
SAM actually does not model storage for PV systems. So if you want to model a PV system with storage, you would need to use a different model.
Okay. And how many types of storage are there with the parabolic? Only TES, or there are others too?
Thermal energy storage systems that use either the HTF from the solar field as a storage medium, or a separate fluid as the storage medium, but they're fluid-based storage systems.
Okay.
Our next question comes from Mr. Eric Rothenberg. Sir, go ahead with the question.
Hi, Paul. I'm wondering, can we do a search or an optimization for an internal rate of return that's if we're like modeling a PPA?
You're sort of faded out there, but I think...
Oh, I'm sorry. Let me repeat. Can we optimize or search a desired internal rate of return for a PPA?
Yes, you can set up a parametric analysis for any of the cost or financial parameters as well. So you could plot a similar graph of internal rate of return versus some variable of interest using the same technique.
Okay.
And our next question will be from Van Nguyen. Your line is open.
Hi, Paul. This is Van. I have a question regarding the power cycle. Is there any way to separate the power cycle from the SAM in general? We want to be able to model the power cycle using our own performance curve, the steam performance and also all the aux load. Is it possible?
Okay, so the question is whether, if I understand correctly, you would like to use the solar field model in SAM and feed the thermal output of the solar field into your own power block model. Is that correct?
Yes, the solar field and the molten salt storage system.
And the storage, yeah. So the answer is sort of. Because the solar field and storage system operate, they interact with the power block. hourly output of the solar field and thermal storage. It reports, I think, the temperature levels of in thermal storage. So you can extract those intermediate variables from the hourly outputs and use them in your own model. But the problem is that as you know, when SAM simulates the system, it's deciding whether and when to defocus collectors in the field and when to deliver energy to storage or from storage based on the power block capacity. And so if you disconnect, if you use the outputs from the storage model and the solar field model in that way, your results might not be exactly what you're expecting.
And once again, to ask a question, please press *1 on your touch-tone phone. One moment, please. Once again, you may press *1 for any questions or comments.
Okay, I think I'll take a couple of these questions from the written questions. Here's one that's, what is the maximum number of variables that we can modify by parametric analysis? And there's no maximum. I mean, I imagine there's some maximum, very large number. But as I mentioned, you don't want to specify too many variables, or it'll take forever to run the simulations. We already saw in this example with 28 values and 2 variables that it's taken several minutes to run simulations. So the number of variables is limited by simulation runtimes, not by any limit of the software. So if you wanted to let it run overnight or for a few days, that's to run a large number of variables. That's certainly possible. Here's a question about outputting raw data from DView. I can spend a moment, because this is also related to the question about using data from the solar field model in the power block model. There are a few different ways you can export data from the simulations. One is on the results page. If I click Tabular Data Browser and then Hourly Data, here's a list of output variables that are available for export through this method. And so I can see, here's the field output, and here's energy delivered to the power block from both the solar field and storage. The collector, the incident, Q incident total is that collector DNI times cosine theta that we were discussing earlier. It has a different name in this interface. So once you've built this table, you can export the data either by clicking Send to Excel, save it as CSV, or copy to clipboard. It's also possible to export the data directly from DView. So if I'm displaying the collector DNI cosine theta, I can just right-click and export data. And this exports whatever data is visible in the graph. So if I zoom in to just 1 month, or just a few days, then it would export only the values for the days that are shown in the graph. Here's a suggestion for assigning the maximum DNI value automatically, so you wouldn't have to go through this process. That's a suggestion that we received. I'll make note of it. Here's a question about importing variables to a parametric setup, and the question is, can you import a table of linked variables into a parametric simulation setup? And the answer is yes. It's a little bit involved. I'll touch on it when we talk about the Excel exchange feature. So it is possible to set up a table of variables in Excel and then have Sam read it into a parametric variable. So if you stick around for the rest of the session, we'll come to that later. Another question on linking parametric variables. Can you link more than 2 parametric variables? Yes, you can link more than 2 parametric variables. Okay, so the questions that I'm ignoring for now, I will write up answers to and post later, along with the questions from yesterday. Okay, so let's finish this up. Now we have results from our parametric simulation for the 2 variables, solar multiple and storage capacity. And if we return to the results page, I'm going to just create a new graph for this. So rather than starting from one of the built-in graphs, I'm going to add a new graph. And I'm simulating parametric results. I want solar multiple as the X value. And I'll choose a line plot. And we're going to choose it versus, we're going to plot the nominal LCOE versus solar multiple. And then up here, and we don't need to see the graph data for now, so I'll click Hide Graph Data. So now we have one of these curves for each of the storage capacity. So each color represents a different storage capacity, and I can find the combination of solar multiple and storage capacity that results in the lowest LCOE from this graph, or if I have a particular storage capacity in mind, I can find the solar multiple for that capacity that results in the lowest LCOE. Now, one thing that this graph shows me is that for the TES capacity of 12 hours and maybe 8 hours, so the dark purple and the light green curves, I'm not sure that I've reached the maximum with a solar multiple of 2.5. So I'm going to need to run a few more values out here to see if I've reached the minimum of this curve. I don't know if this curve continues to go down or if it curves back up once I go beyond a solar multiple of 2.5. Since I only simulate allowed values up to 2.5 in the parametric setup, I can't see beyond that value unless I add additional values. So maybe I should go out to 3.5 so that I can get a graph that goes out to 3.5. So this is sort of an example of this optimization technique. Is I find it best to start off with a small number of values and then to plot graphs and then sort of use an iterative process to come up with the range of values that I need. If I'm interested in 12 hours of TES, for example, then maybe I can remove these values, 1, 1.25, and 1.5 from this list to minimize the number of simulations that I need to run. So I could just do that by selecting the value in this table and then clicking Remove. And so then I'm back to a more reasonable number of values. So I won't go. I won't do that now, but hopefully you see the technique. This whole process for optimizing the solar field is described in Help on the solar field page under the Sizing the Solar Field topic. So if you want to look back and see how I did this, the instructions are here in Help. And again, I'll be posting a description of what I just demonstrated on the SAM website later today or tomorrow. So you can refer to the instructions there as well. I did want to come back to the question about IRR. So let me disable this simulation and make sure that I have the solar multiple of 1.25, which I found was optimal for a system with no storage. So I want to make sure that I have system with no storage and solar multiple 1.25. Okay, so this is a reasonable system. If I wanted to look at plot a graph of internal rate of return, that's internal rate of return is available here. So I could look at IRR versus IRR. Well, I took out the parametric analysis. So with the parametric results, I could have plotted similar. Instead of plotting LCOE versus solar multiple, I could have plotted IRR versus solar multiple. But it's also possible to explore some of the financing variables using sliders. So you don't have to, because the financial calculations don't require re-simulating the system. So if you remember yesterday, I mentioned that SAM, there's sort of two parts to the SAM model, the performance model and the financial model. And the financial model, the only performance metric that the financial model uses is this annual energy value. So to run the to generate results for different scenarios from the financial model, SAM doesn't have to rerun simulations. So for that reason, the financial results can be explored using these sliders. So for example, I could maybe look at solar field cost and storage cost, add those as sliders here. And then I'm showing here a bar graph of internal rate of return, which isn't too interesting on its own, but I can adjust the solar field cost variable here dynamically using these sliders and see how it affects the internal rate of return, which in this case it doesn't. I should change the label here so it's not confusing. Maybe if you look at the financing assumption and change the debt fraction or discount rate, so I can add these sliders and make adjustments to see their effect on an output. And obviously these are not affecting the IRR, but the net present value. I'll put okay. So now, as I adjust, well, there's a few things going on. One is that the scale is changing, so I'm not getting a visual feedback as I change the slider. So if you're going to use sliders, you want to fix the y-axis. So to get to this window, I'm right-clicking the graph and then clicking Edit, and you have all these. You can control the parameters of the graph. Obviously, it takes a little trial and error to do this on the fly. Not the best thing to do while you all are waiting, but just want to make sure that you see how this works, and you can experiment with it on your own. So as I change the sliders, the graph is changing. If I click Show Graph Data, I can see the numbers change as well. This is another option for this kind of analysis involving multiple values of variables.